Asymptotes. In this sketch, we have an example of a curve and an asymptote. An asymptote of a curve is a straight line which approximates the curve as the curve tends to infinity. It's a straight line, or an invisible straight line, that the curve will never touch. Only certain types of curve have asymptotes. For the most part, it is only curves with equations of the form y equals u of x over v of x, i.e. in the form of a fraction. However, there are other curves with asymptotes. For example, y equals e to the power of x, y equals the natural log of x, and y equals the inverse tan of x, which we have met previously. There are two types of asymptote on our course: vertical and horizontal asymptotes. Vertical asymptotes. The vertical asymptotes of y equals u of x over v of x are found by putting v of x equal to 0, so basically the denominator equal to 0. If x equals a is a solution of this equation, then the vertical line x equals a is a vertical asymptote of the curve. It acts like a vertical line that the curve tries to get over or under, but which cannot cross. So for example, here's our x-axis, here's our y-axis. We see this is one part of our curve and another part of our curve, y equals f of x over g of x. And this is the line x equals a, and this is a vertical asymptote. So the curve gets closer and closer and closer and closer and closer to this line, but it never touches it. And likewise, the other half of the curve gets closer and closer and closer and closer to the line, but never touches it. Example: find the vertical asymptote of the curve y equals 2x plus 3 over x minus 1. So what we do is we put the bottom line, the denominator, equal to 0. So we let x minus 1 equal 0, and then we solve for x, so we bring the minus 1 over the equal sign, so x is equal to plus 1. So this is the vertical asymptote of this curve. Asymptote limits. To find the horizontal asymptotes of a curve, we need to be able to work out limits of the form the limit of u of x over v of x as x approaches infinity. That's positive infinity. To evaluate these, we need the following special limits. So here are some special limits. The first one, the limit of 1 over x to the power of n as x approaches infinity is equal to 0, as long as n is greater than 0. So for example, we could have the limit of 1 over x to the power of 2 as x approaches infinity equals 0. So long as whatever we have here in place of the n, so 2, 3, 4, 5, 6, and so on, so long as it is positive, greater than 0. Number 2, the limit of r to the power of x as x approaches infinity is equal to 0, if r is between minus 1 and 1. So for example, we could have the limit of 1 over e to the power of x as x approaches infinity, which can actually be written as the limit of 1 over e to the power of x as x approaches infinity equals 0, as 1 over e is in between minus 1 and 1. So the reason that this can be rewritten as this is because 1 to the power of anything is still just going to be 1. So we can apply the power to the entire fraction. In addition, we have a number of rules for calculating limits, as the variable, so as the x usually, tends to infinity. Rules of limits. Suppose the limit of u of x as x approaches infinity and the limit of v of x as x approaches infinity are real numbers and k is a constant. Then the limit of k as x approaches infinity is equal to k. The limit of k multiplied by u of x as x approaches infinity is equal to k times the limit of u of x as x approaches infinity. So basically you can just take this constant and put it in front of the limit. The limit of u of x plus or minus v of x as x approaches infinity is equal to the limit of u of x as x approaches infinity plus or minus the limit of v of x as x approaches infinity. So basically you can just break this apart into two separate limits with a plus or a minus in between. The limit of u of x multiplied by v of x as x approaches infinity is equal to the limit of u of x as x approaches infinity multiplied by the limit of v of x as x approaches infinity. So similar to number 3, you can break this apart into two separate limits with brackets. And the limit of u of x divided by v of x as x approaches infinity is equal to the limit of u of x as x approaches infinity divided by the limit of v of x as x approaches infinity. So again, similar to 3 and 4, you can break it apart into two separate limits. But this number 5 is only as long as the limit of v of x as x approaches infinity is not equal to 0. So you just cannot have our denominator to be 0. If a limit is initially indeterminate, so generally infinity over infinity, then we can use a combination of the special limits and rules to calculate the limit. This generally involves dividing above or below by the dominant term. So the dominant term being the highest power of x, or if x is in the index, then the power with the largest base. We also have to be able to calculate a limit in the form of f of x as x approaches negative infinity. Rule 6 deals with this. So the limit of f of x as x approaches negative infinity is equal to the limit of f of minus x as x approaches positive infinity, i.e. substitute minus x for x in the function and take the limit as x to the power of positive infinity. So basically just swap the signs between the limit and the x. F of x maps to 2x plus 3 over 3x plus 1. Part 1. Find the limit of f of x as x approaches infinity. So again, if a limit is initially indeterminate, so generally infinity over infinity, which this one is, because if we were to substitute infinity in place of this x, it would be 2 multiplied by infinity plus 3, which obviously would be infinity. And if we were to substitute infinity in place of this x, it would be 3 multiplied by infinity plus 1, which again would be infinity. So it would give us infinity over infinity. So again, we're going to use a combination of the special limits and rules to calculate the limit. And this involves dividing above and below by the dominant term. And the dominant term being the highest power of x. So the highest power of x in both the numerator and the denominator is x. So we want to divide the numerator and the denominator by x. So another way of doing this is by multiplying by 1 over x. So dividing above and below by x is the same as multiplying by 1 over x. So 2x multiplied by 1 over x will just give us 2. And 3 multiplied by 1 over x is just 3 times 1 over x. 3x times 1 over x will just give us 3. And 1 times 1 over x will just give us 1 over x. So now we have the limit of 2 plus 3 times 1 over x over 3 plus 1 over x as x approaches infinity. So the bigger the x gets, the closer 1 over x will get to 0. So we're substituting in place of the x infinity. So the bigger that this x will get, the closer that 1 over x will get to 0. So this becomes 3 multiplied by 0. So our numerator will be 2 plus 3 times 0. And likewise on the bottom, this 1 over x will get closer and closer to 0. So it'll become 3 plus 0. So 2 plus 3 times 0 is 2. And 3 plus 0 is 3. So the limit as our function approaches infinity is 2 over 3. F of x maps to 2x plus 3 over 3x plus 1. Part 2. Show that the limit of f of x as x approaches minus infinity or negative infinity is equal to the limit of f of x as x approaches positive infinity. So the limit of f of x as x approaches negative infinity is equal to the limit of f of minus x as x approaches positive infinity. So what we have to do is replace each x with minus x. So we swap each of these x's for minus x. So the limit of 2 times minus x plus 3 over 3 times minus x plus 1 as x approaches infinity is equal to the limit of minus 2 plus 3 times 1 over x over minus 3 plus 1 over x as x approaches positive infinity. So what we've done here is divided above and below by x. And that's the same thing as in the previous slide as multiplying by 1 over x. So 2 times minus x multiplied by 1 over x is just minus 2. And 3 times 1 over x is 3 times 1 over x. And 3 times minus x times 1 over x is minus 3. And 1 times 1 over x is 1 over x. So now we let x approach infinity. So we swap each of these x's for infinity. And again, as similar to the last slide, the closer that x gets to infinity, the closer that 1 over x gets to 0. So we end up having 3 times 0 and then minus 3 plus 0. So we have minus 2 plus 3 times 0 over minus 3 plus 0, which gives us 2 over 3. So this is equal to the limit that we got in the previous slide, which is the limit of f of x as x approaches positive infinity. So we have shown that the limit of f of x as x approaches negative infinity is equal to the limit of f of x as x approaches positive infinity. Limits as the variable tends to infinity, although in a slightly different context, will be examined again in a later chapter. Horizontal asymptotes. A horizontal asymptote is a horizontal line that approximates a curve as the curve tends to infinity. A curve representing a function can have at most 2 horizontal asymptotes. One on the right as x tends to be positive infinity, and one on the left as x tends to negative infinity. The diagram opposite shows the curve y equals 2e to the power of x plus 1 over e to the power of x plus 2, which has the line y equals 2 as a horizontal asymptote on the right, so as x approaches positive infinity, and the line y equals a half as a horizontal asymptote on the left as x approaches negative infinity. So here's our curve, y equals 2e to the power of x plus 1 over e to the power of x plus 2. And as x approaches positive infinity, we can see that the curve gets closer and closer and closer and closer and closer to the line y equals 2. And as x approaches negative infinity, we can see that the curve gets closer and closer and closer and closer and closer to y equals a half, but never ever touches either of the lines, never crosses either of the lines. So the horizontal asymptotes of the curve y equals f of x, when they exist, are on the right, y equals the limit of f of x as x approaches positive infinity, and on the left, y equals the limit of f of x as x approaches negative infinity, which we know now that we can rewrite as y equals the limit of f of minus x as x approaches positive infinity. You should note the following. Knowing the asymptotes of a curve is very useful when it comes to sketching a curve, as the asymptotes provide a frame for the curve. Polynomial curves and trig curves do not have asymptotes. We generally only consider asymptotes for certain curves of the form y equals u of x over v of x, so fractions. A rational curve, so a fraction, is one of the form y equals u of x over v of x, where u and v are polynomials in x, so in terms of x. For the horizontal asymptotes of a rational curve, you should note the following cases. If the degree of u of x, so the numerator, is greater than the degree of v of x, the denominator, then the curve will have no horizontal asymptotes. If the degree of u of x is equal to the degree of v of x, so if the numerator and the denominator have the same power of x, then the curve will have the same horizontal asymptote on the left as on the right. And if the degree of u of x, the numerator, is less than the degree of v of x, the denominator, then the x-axis will be the horizontal asymptote for the curve both on the left and on the right. Find the horizontal asymptote, or asymptotes, if any, of the curve y equals 3x squared plus x minus 1 over x squared plus 2. As the top line and the bottom line both have a degree of 2, so they both have x squareds, there will be a horizontal asymptote, but it will be the same on both sides. So we have y equals 3x squared plus x minus 1 over x squared plus 2. To work out the right horizontal asymptote, we say y is equal to the limit of 3x squared plus x minus 1 over x squared plus 2 as x approaches positive infinity. So we want to divide above and below by the highest power of x. So the highest power of x is x squared. So we divide the numerator by x squared and divide the denominator by x squared. So this is the same thing as multiplying by 1 over x squared. So 3 multiplied by 1 over x squared is 3. X multiplied by 1 over x squared is 1 over x. Minus 1 multiplied by 1 over x squared is minus 1 over x squared. X squared multiplied by 1 over x squared is 1. And 2 multiplied by 1 over x squared is 2 multiplied by 1 over x squared. So we have y equals the limit of 3 plus 1 over x minus 1 over x squared, all divided by 1 plus 2 times 1 over x squared as x approaches positive infinity. So the closer that this x value gets to positive infinity, the closer that 1 over x gets to 0. And likewise for this fraction and for this fraction. So we end up having y equals 3 plus 0 minus 0 over 1 plus 2 times 0, which is really 3 over 1, which is 3. So y equals 3 is the horizontal asymptote on the right. So now let's have a look at the left horizontal asymptote. So y equals the limit of 3x squared plus x minus 1 over x squared plus 1 as x approaches minus infinity. So we're going to change this minus to positive, and then we have to change all our x values to negative, but we also have to divide above and below by the highest power of x, which is x squared, which is again is the same thing as multiplying by 1 over x. So 3x squared multiplied by 1 over x squared gives us 3, but then we change the 3 to minus. X multiplied by 1 over x squared gives us 1 over x, but we change this plus to minus. Minus 1 multiplied by 1 over x squared gives us minus 1 over x squared, but then we change this minus to positive. And likewise for the denominator, we multiply x squared by 1 over x squared and we get 1, so we change this 1 to a minus. And then we multiply 2 by 1 over x squared, which gives us 2 times 1 over x squared, so we change this plus to a minus. And likewise, all of these signs will change as well. So similar to the right horizontal asymptote, for each of these x values, the closer that they get to infinity, the closer that the fraction itself will get to 0. So that's how we get 0 for each of these. So minus 3 minus 0 plus 0 is just minus 3. And minus 1 minus 2 times 0 is minus 1 minus 0, which is just minus 1. And minus 3 divided by minus 1 gives us 3. So y equals 3 is the horizontal asymptote on the left. So we were asked to find the horizontal asymptotes of the curve y equals 3x squared plus x minus 1 over x squared plus 2. And y equals 3 is the horizontal asymptote on the right of our curve. And y equals 3 is the horizontal asymptote on the left. So here we can see our curve drawn in. This is the curve of 3x squared plus x minus 1 over x squared plus 2. You can see this is the line y equals 3. And we can see that on either side of our graph, our curve is getting closer and closer and closer to the line y equals 3, but it will not actually cross it.